last time we talked about composing vector fields, and the first step in understanding that operation is to view a vector field in the following equivalent way. So we view it as a linear map. X, which takes the set of smooth functions to itself in the only way that makes sense. So we take f to its image, xf, which is a function whose value at p is the derivation given by evaluating x at p acting on f. And so not all such linear maps are vector fields. We also need them to satisfy the product rule. So x acting on a product of two functions, which is again a function, is x acting on the first times the second plus the first times x acting on the second. OK, so when we talk about linear maps from a vector space to itself, you can compose them. So xy makes sense as a map. Just the composition of the map defined by the vector field y with the map defined by the vector field x. So x times y acting on f. So this is a vector field that acts by y acting on f to give a new function, and then x acts on that function to give the resulting function, the end function. All right, so this makes sense as a linear map, but is not a vector field. It fails to satisfy, as we saw in an example, the product rule. Okay? In general, this just does not hold. So vector fields are not closed under composition. So that was a disappointment, but one can retrieve something important from this disappointment. Understanding it, we'll see eventually that, or very soon, that even though xy is not a vector field, if you take xy and subtract yx, this is a vector field. Okay, and this is easy to prove from the definition. As you might guess, the problem terms for xy composed this way and yx composed this way cancel each other out. Okay, so let's see that happening. So we started on this journey last time, but let's finish it. So what's at stake here? We know that this is a linear map. This is a difference of two linear maps is a linear map. And so we have to verify that this satisfies that product rule. So we have to apply this to a product of two functions and hopefully get what the product rule demands. All right. And so we start along this road, and we have x times y acting on fg minus y times x acting on fg. This is just by definition of what these maps are. So it's this acting on this minus this acting on this, and this acts on a function in this way, just composition as described there. All right, and now we can use the fact that x and y are vector fields themselves. So y satisfies the product rule, and x satisfies the product rule, and we're free to write down what that means. So when we do that, we have x, and then we have y acting on this product by the product rule. So we have y acting on f times g plus f times y acting on g. Okay? And then we subtract y, and then we apply the product rule for x, and we get x acting on f times g plus f times xg. Good. All right. And so what's in the brackets is essentially as much of, I mean, there's nothing else we can do there. We don't know anything more about y besides it's a vector field. So we have to use our knowledge of what's on the outside here, so x. So now x is acting on, well, a sum, so we can split that up. And then each of the summons is a product of two functions again. Right? It's this function times this function. So we apply the product rule for x again for each summoned. All right. And so we get x acting on yf times g plus yf times x acting on g. That's the x acting on the first term here. And then we'll get 6 more terms. So let me write them down. One sec. No, I just. All right, and then, so these are the first 4 terms, applying x, and then we apply y, and we get 4 more terms. Okay, and so now we get some cancellation. We have yfxg, and we have yfxg with a minus sign, so these two cancel. And then we have xfyg, and then we have minus xfyg, and these cancel. And we're left with 4 terms, which we can reorganize. In the following way. So what is acting on G here? Where's G? All right, so we have xy acting on f minus yx acting on f times g. Okay, so we can write that as xy minus yx f times g, right? So I just took this term and this term and wrote them like that. Good. And then we can probably guess what we have. Plus f, and then we have xy minus yx acting on g, so we'll put it like that. And that would be the remaining terms, so I shouldn't have to look very far. Here. Okay? Which is, so if you go from the starting point to this point, this is exactly what would be required if this object was supposed to be a vector field. Okay? It satisfies the product rule. So, so now so we have a rule. We have two vector fields, and we produce a third one. All right. OK. So we're going to give this a different name. So square bracket xy. So this is the Lie bracket of x and y. And it's a new vector field. And it's got a very simple definition. And it's got some simple properties that it inherits from its simple definition, which are useful to state. So properties. First, this is linear in each argument, so it's bilinear. Two, we know from just our simple description that if we reverse the order in our product, we get a minus sign. Third is an interesting algebraic relationship. So you can view this. So we have three vector fields. We take the Lie bracket of y and z. We get a new vector field, which we can take the bracket of with respect to x. OK? And then if you cyclically permute the things that appear here, you get 0. So this is something which you may see in other contexts. So this is the Jacobi identity. And then the fourth property worth mentioning, which follows from the definition and the fact that all these things satisfy the product rule, is that, well, we get the following formula. Given two vector fields x and y, we can multiply each by functions to get new vector fields. OK? So this is a new vector field. This is a new vector field. And we want to know how so can we take f and g out? OK, so the answer is, well, there is a term like this, but there are other things to consider. OK? Certainly, if f and g were constants, we could just take them out by the first property. Right? But they're not. That must mean that the other properties involve derivatives, yeah. Something acting on these functions. And so the remaining term is x acting on g times, and the result has to be a vector field, right? So it's plus and then y. And then we have g and then y acting on f times x. So we can pull them out, but we get some function times y involving the derivatives of g with respect to x and just f itself. And then we get some multiple of x involving y acting on f. That's a function times g.
Is that a minus?
That's not an equal sign. Yeah. It should be minus. Very good. Good intuition. All right. All right. All right. I think I can't make any more mistakes with those three signs. All right. Well, I can. I could cyclically permute them. All right. So one nice feature that this operation inherits from this fourth property in particular is that it's easy to compute the Lie bracket of two vector fields in coordinates. Okay, this is an important point. So in coordinates, we have the following. So if we have two vector fields, x and y, we know that we know what these look like in coordinates, right? This is some function times d by dxi, right? And we have I equals 1 to n of these, and y is a similar object. Right? Good. So if we understand the coordinate expressions for x and y, we can also deduce the coordinate expression for their Lie bracket. Okay? Like any vector field, it should be a linear combination of the d by dx's. Right? So it should look like sum j equals 1 to n, and then we have some coefficient, and then we have d by dxj. So what is this coefficient function? So it's the following thing, which is easy to compute. So it's a sum over from I equals 1 to n, and then we have xi times the partial derivative of yj with respect to d by dxi, minus yi, the partial derivative of xj d by dxi. Okay? So I feel like maybe I'll put a bracket there. Good. So this is very easy to compute in coordinates. You just have to take partial derivatives of the coefficient functions and put them together in this package. Okay? Let's just do it for a simple example, which we will come back to later. Good. So let's look at an example. Let's suppose we have a vector fields on R2. And the first one is just d by dx1. And the second one is d by dx2 times x1. Okay? So this formula tells you right away that if both this set of coefficient functions are constant, then we're going to get 0. Right? We're going to be taking partial derivatives of constant functions all the time. So that's why we have the actual function in the second vector field. So it tells you that if you do the Lie bracket of d by dxi, d by dxj, you just get 0 all the time. Okay, those are all 0. All right. But if you have actual coefficient functions, then you don't necessarily get that. And so if we compute this, well, I'm just going to give you the answer, and you can check that. So this is an exercise. Here's to plug it into that formula. Okay? All right. So it is as computable as things on manifolds can be. In local coordinates, we know how to write down the answer. Okay? Very good. Which leaves us with one question. What is this object which we've defined? So it has all these nice properties. We know how to compute it, but we don't know what it's measuring or what it represents. Okay? So it's not clear why we would want to compute it. So let me tell you the answer, and then we'll justify what's in the answer. So it is a vector field, that much we know. So if we evaluate it at P, we get an element of the tangent space to M at P. Right? And so how should we interpret that? We will interpret this as the derivative of y at the point P in the direction of x. Okay, so this is some kind of directional derivative of one vector field with respect to another. All right, so let's try to make sense of that. Which is, I mean, at first sight, it should be curious, right? It looks like x and y are playing essentially the same role here. They are. But somehow this should be interpreted as the derivative of y in the direction of x, which means it's also the derivative of x in the direction of y with a minus sign. Okay? So somehow those two quantities have to be related just by the properties of this map. So it's a bit of a mystery how to get from Q to A. So let's unravel it. Let's first remind ourselves what we know about directional derivatives and try to enlarge that picture so that it eventually involves vector fields. So what do we know? We know that the derivative of a function in the direction of a vector field well, we have a name for that. That's just x evaluated at P acting on F. Okay? This interpretation motivated our abstract definition of a tangent vector. All right, so that's not helping us. That's just a symbol, right? All right, so we did have a way to compute this using calculus, okay? So we know that we can compute this as a derivative, so it's d by dt at t equals 0 of f of gamma of t when gamma is in a smooth curve, and its value at 0 is p, and its tangent vector at 0 is x of p. Right? So we have a way to view this in terms of calculus. All right. Good. Right. So does that work for vector fields? Not quite yet. All right. The thing is that this is a real valued function. If we put a vector, if we replace this by an x, that's just a collection of vectors along the image of the curve, right? And so we don't know, calculus doesn't tell us what the derivative of that is. Okay. So in order to resolve this problem, the first thing we're going to do is choose a curve. There's a natural choice of curve here with these properties. It's a curve given by the flow of x. So let phi xt be the flow of the vector field x. So in local coordinates, we know how to find this. It's, well, we have a recipe. It's a system of first order ordinary differential equations. All right, and what do we know about this? We know that, so now we're going to set gamma of t equal to phi x t acting on p. Okay? So what does that tell us? That tells us that, well, so if we evaluate this at 0, so gamma of 0 is equal to phi x0 acting on p. If you plug in t into the flow, you get the identity map, right? So this is p as desired. Right? We want our curve to go through p at t equals 0. And gamma dot of t, If we take d by dt of this, well, that's like going from the solution of the differential equation to the functions defining the differential equation, which comprise the vector field. So and that should be at 0. Okay. That is the system of equations. Okay. So that's what we want. So this is a good curve. And then we can define what we're interested in, this directional derivative, with this playing the role of gamma. Okay. And now we're going to do something slightly different. Instead of writing down just the derivative with respect to t, I'm going to write it as a limit of difference quotients. Okay? So it's equal to, this is just taking the place of the derivative. This is the definition. And then we have f at phi x t of p minus f of p over t. Okay? Good. So what's our first guess for the derivative, the directional derivative of y at p with respect to x? So we need to interpret our answer. What does this mean? Okay? So our first guess is to just replace the f's there with y's. I want to take the derivative of y. So we want the limit as t goes to 0. And then we have y evaluated at phi x t of p minus y at at p over t. Okay? So we still, unfortunately, have this same problem that we did before, but now we have a fix for it. So the problem is, that that doesn't make sense. What's wrong here? These two objects belong to two different vector spaces, right? So the problem is that y at phi x t of p belongs to the tangent space to M at phi x t of p. And y of p belongs to the tangent space to M at p. And those are two different vector spaces. So you can't subtract something from here and something from here. So that doesn't make sense. Does that make sense? Does that nonsense make sense? All right. So how are we going to resolve this problem? We have to move something. We have to move, in order for this to make sense, we have to move one of these vectors so that it lies in the same vector space as the other. Okay? Otherwise, we can't subtract them. All right, so here's the fix. Well, we have a natural map which does this. So fix. Consider. So how can we go from one of these vector spaces to the other? Well, we know how to go from this vector space to this vector space, right? We just take phi x t and we apply its derivative. So this is a map derivative at p. I'm going to drop the p's because I have too many symbols. But let me tell you the domain. So this takes tpm to t phi x t of p, the image of m. Okay? So this is a map from this vector space to this vector space. Okay? So then the question is, does it identify the two spaces? We don't know. It could be the zero map, right? But we know it's not. How do we know it's not? So let me just recall the fact. So if you take Well, let's look at the identity map on M. We know that that's phi x of 0. Yes? For any flow, if you plug in parameter 0, you get the identity map. We also have the group law for the flow. So this is phi x of, let's say, minus t plus t. That'll get you to 0. And the group law tells you that that's a composition. So that's phi x at minus t composed with phi x at t. All right. And so if we take the derivative of these equations, so as maps, then we get the identity map on, so this is a map on TPM. And then the chain rule tells us what the derivative of this is. This is the composition of the derivatives, right? So it's d of phi x of minus t and phi d, and then composed with the derivative of phi xt. And so this tells us something about this map. It tells us, well, if this is involved in a composition, which is the identity map, then this map is an isomorphism. Okay, it's 1-to-1 and onto, and its inverse is this. Okay? That's what this equation is telling us. So let's just shorten that. That tells us that d phi tx is invertible, and its inverse is d phi x minus t. Okay. So this is an isomorphism, and then we have a name for its inverse. Okay? All right, so now we're going to fix this problem. We're going to use these maps to move one of these vectors to, let's just pick this as our target vector space, so the one that this belongs to. So now our second attempt, which is successful. This, by the way, this is why we used not just a curve gamma, but the flow of x. So we have these diffeomorphisms coming. Right? We don't without that choice, we wouldn't have a natural choice of diffeomorphisms. All right. All right. So now to our final version of the directional derivative. We have the limit as t goes to 0. And then we have, so we're just going to move this one to the tangent space to M at P using this map, which goes from here, where that thing lives now, to here, where we want it to live. So we have d phi x minus t acting on y at phi xt of p. So now that's in the tangent. So where is this? This is in the tangent space to M at P. And this is the tangent space here, and this moves it back. Minus y at P over T. Now this is a well-defined object. What kind of object is it? This is an object of calculus. So all the action is taking place in this one vector space. Yes? All these objects live in this vector space. So this is so how do you think of this? So let's identify this with Rn. Okay? We have standard coordinates. Let's think of this as Rn. So the numerator is a path of vectors in Rn. So it's a curve. And we can take its derivative like we did for curves in multivariable calculus, right? So the result, that's what this is. So this is n. What's the derivative of a curve at a point? It's a new vector. Yes? And so that will be our answer. And now we have a directional derivative. So this is the name for it. Okay, this is a symbol. and we're evaluating it at p. Okay, so this symbol has a different, I mean, we could have started this with, we could have started a discussion with the motivation of defining directional derivatives of vector fields and come up with this as we did. And this is called the Lie derivative of y with respect to x, and we evaluated it at p. Okay, that's what that symbol means. All right, so now let's compute it in an example. So we see that there's an inherent difficulty with proving this, or to computing this. It looks like we have to find the flow, which we know involves integration, which we know unless your instructor takes the time and is not sadistic, might not be possible, right? You can't always integrate everything. Okay? But let's do an example where you can integrate something, and then we'll, even in coordinates. And then we'll resolve this problem with a beautiful identity. All right, so here's an example. We'll do the same example that we did before. Okay, so we saw that if we took the Lie bracket of these two vector fields, we got d by dx2. That was the claim. I left that as an exercise. Now let's compute the Lie derivative of y with respect to x. Okay, so what we need is the flow of x. Okay, so x is very easy to integrate in this case, because I'd just be punishing myself if it wasn't. So it's, well, it's just x1 plus t x2. That's the flow. You can write down the differential equations if you don't believe me, but that's the answer. And so now we need the derivative here. Right? That's also easy. So d by xt. Well, it doesn't matter. It's always, right? You're taking derivatives with respect to the x's here. So you get 1, 0, and 0, 1 for all t. Okay? So now if we compute Lxy and evaluate it at the point x1, x2, we have the limit as t goes to 0, and then 1 over t. And then this should be a path of vectors in a vector space. So we get this acting on y. Well, this is the identity map, so we just get y, right? So we get, but evaluated at the image of the flow. So we get not x1 d by dx1, we get x1 plus t d by dx1. Yes, d by dx2. And then subtract y evaluated at the point. So that's minus x1 d by dx2. So you agree that you can interpret that as a path in a vector space, right? This vector space happens to have basis d by dx1, d by dx2. It's okay? It's a tangent space. All right, and this is easy to compute. This cancels with this. We have t d by dx2. We have a 1 over t. The t's cancel. And so the limit is easy to take because there's no t's. And we get d by dx2. OK? So this is the same thing that we got when we took the Lie bracket. Or that if you do that exercise, you'll see that you get the same answer. And that's no accident because we have the following beautiful theorem. that this thing we kind of constructed by default, the Lie bracket, which is a new vector field, is the same as this. All right, so as an immediate corollary, we can compute this in coordinates just by taking partial derivatives, right? So we can compute Lxy in coordinates without computing the flow. Phi xt. Which we can't always do. Okay, so this is, we can always take partial derivatives. All right. So why is this true? They don't, I mean, they didn't come from the same place. The symbols don't look that similar. It's kind of a mystery. Okay, so let's discuss the proof. All right, good. So any proof needs some kind of version of Taylor's theorem, any complete proof. So we will use the following tool, which is Taylor's theorem in disguise. Okay. So this is, the book refers to this as Hadamard's lemma. Hadamard. Okay, so for all f and points P and M, there's an epsilon greater than 0. And a function g t of p such that okay, here it is. So let's look at f evaluated at phi x t of p. Okay, so f, we have the flow of a vector field. It defines a curve through the point P, and we evaluate f along that curve. So in terms of objects, this whole thing is just a function of t. Okay? And so Hadamard's lemma tells us that this function of f of t is f evaluated at p, that's a number, plus t times something, this function g. And that works for t less than epsilon. So this is Taylor's theorem for functions of t. We just gave things different names. Well, it depends how you think about it. So it's the constant term and then all the rest. And Taylor's theorem tells you about the rest. Okay? If you keep on doing this, so if you do this to this function, you'll see the first order term in Taylor's theorem, and then you keep on going, you see the second order term, etc. Okay? So we're not going to prove this, but hopefully you're comfortable recognizing this as some version of Taylor's theorem. Okay? Good. Now what does this tell us about g of 0 of p? Well, what should this be? This should be the derivative of something, right? But it should be the derivative of this thing with respect to t. What do we know that to be? That's x at p acting on f. Right? If we take the derivative of this with respect to t at t equals 0, that's by definition what that is. Okay? All right. So I'm going to delay the proof, but we're going to talk about something else. I don't want to rush the proof because it's got some subtle points. Rest of proof next time. Let me tell you that there's many related stories to that theorem. Rest of proof next time. Let me tell a related story to Lie derivatives and Lie brackets. So one can take the Lie derivative of other things besides vector fields. Okay? In fact, one can take the Lie derivative of any tensor with respect to a vector field. Okay? But I'm going to describe what happens when you take the Lie derivative of a K-form. Okay? So let's define the Lie derivative of this K-form with respect to the vector field X. Okay? We're still in session here. All right, so this should be a K-form. Okay? So we're going to evaluate it at P, and it will be the limit as t goes to 0. And, well, what's the bad guess? You evaluate this at phi xt of p, subtract omega at p, and take the derivative, and take the limit as t goes to 0. Right? But they belong to the wrong vector spaces. Now you have to remember where these vector spaces lie. These are the space of alternating k tensors on the tangent space at p, and this would be at phi xt of p. So we have to change that. And here we have a very simple operation. We have the pullback. So we have phi minus tx star of omega, and that lies in the right vector space. Okay? Okay. So this is a directional derivative of omega in the direction of x. Now, what is the analog of this? So you can think of this as a simple formula for this, if you like. Okay? In coordinates. What is the analog of that in this case? It's called Cartan's magic formula. Okay, and it says the following. Perhaps you've used it, I don't know. It says the following. All right. So if you want to compute this vector field, it's as simple as doing the following. Or sorry, this P form, K form. You take omega, so omega is a K form. So you can put x in its first argument. Okay, now what is that? That's a k minus 1 form, but you want a k form. So how do you get from k minus 1 forms to k forms? You put a d there. Okay, that's not the rest. That's not the only part of the formula. And then we do it in the opposite order. We take d of omega. No. We take d of omega. That's a k plus 1 form. Okay, and how do we make it a k form? Well, we put x in its first spot. Does that make sense? So these are very simple operations in local coordinates, right? You just insert a vector into the first argument. Okay, that's easy. And then you take the exterior derivative. That's just a collection of first order partial derivatives and wedge products. So this is very simple, but this is not, right? You need the flow here. Okay. All right, so next time we'll prove this identity and go on from there.